1 minute, I think I'll just give this one play. Yeah. Okay, sure. Yeah, I think that's fine. Okay. Yeah. So, yeah, good afternoon. I think just start from where we left actually. We were looking at the construction of the Bayesian networks. So once we have a structure, we have a process structure, or from the topology or from the data, once you understand the correlation between the variables, you can come up with some flow network structure actually. So here you can see the same, the splitter network, one can come up with, by looking at the flow diagram, one can come up with the network structure of it. So here each node, as I reiterate, actually each node is a random variable. Actually, each has its own distribution. It can be of any choice of your distribution which you are interested to fit. Okay. So each node has a distribution and it follows the nodes corresponds to the random variables and the edges corresponds to the direction of the flow, like how the flow is entering actually. So how the 1fx6 or 5fx6 or 2fx4 actually kind of. So one can come up with the structure. Okay. So let's suppose this is, you are coming up with the network structure, then there are chances of like one advantage of Bayesian network that it can give is, what if your measurements are very noisy, that this particular measurement which is highly noisy actually kind of. So what happens then when I'm trying to construct a network structure of this, if this particular variable is highly noisy, so that can penetrate, that effect of the noisy can affect into all the particular variables. Okay. So will a generic regression solves the problem? A conventional least squares regression. It has effect. We cannot solve it if, if one particular variable is highly noisy. You need to use some additional extensions of it actually. So here one can modify this structure actually kind of. One can not modifying the structure. One can come up with additional variables which are called hidden variables actually. We can come up with something called hidden variables. So where you can see initially the previous one is directly connecting with respect to measurements. You have measurements and measurements are directly affecting the variables. But now I am saying that my measurements are noisy. All the measurements are noisy because these are sensors which are mounted on the particular reactor and these sensors have huge fluctuations. They can be noisy. Okay, I need to filter out the noisy. Okay, let's suppose I am interested in predicting the y6 variable is my desired interest, and these 5 measurements I am using, these are all highly noisy. So I can come up with some structure of this nature actually, where the blue, these corresponds to the measurements and these are the hidden variables, which are the true state of the system, which we doesn't know, which are the true state of the system, which are hidden and which are true state of the system. So it's like you are having a y1 sensor measurement here, y1 sensor measurement here, but this y1 sensor measurement, actually the true hidden state is x1. y1 is the actual measurement you are getting, but the hidden state is x1. Okay. Similarly, you have y2 measurement coming from the sensor, but the hidden actual true state is x2. Okay. So similarly, so rather than considering just a measurement, like going with this approach, okay. So actually I can filter the noisy measurements by incorporating the hidden variables. I call hidden variables here. If I just use a regression problem here, that the estimates obtained through parameter regression, least square regression will be wrong actually. I cannot go with it. So I can use something called hidden variables here. So that gives an additional benefit for a Bayesian networks actually. So I can add one more hidden layer. So where I can say that x1, x2 are the noise-free states. Can I able to now, rather than predicting y6, I am interested to predict x6. x6 is a true hidden state, which is unknown. and I use these measurements, filter out and get the hidden states, and I predict the hidden state of X6 in the presence of measurement. So that the noisy measurements, whatever the noisy measurements are there in the sensors, will not affect or influence your state variable, the true state variable. I want to filter out that particular noise, okay. But this comes with additional cost now. Now initially life was easy. You have only 6 variables, all are measured, right? Everything is measured. The only unknown parameters are the relation that we have here. Maybe simple linear model relation. But now we are making life complex, saying that now not only that the parameters are unknown, now you have additional hidden variables also as unknown variables actually. Okay, hidden variables are unknown. So let's see, it's a challenging problem now. Actually, now you can see that the problem complicates it actually. Okay, let's see how we can solve this particular problem. Okay, so these are different structures I'm looking at. I'll look at now this particular structure. If this is the case, how the problem is formulated, it is straightforward. Now I can write a joint density function. Okay, this one. The same way, when I have this structure, now the variables are doubled. There are 12 variables actually, and each has its own independent density functions. So am I going to come up with their independent density functions? That's the challenging actually. Okay, yeah. So yeah, let's look at now. Till now we are looking at structure part. Now the next part, once you design the structure part, which structure you are interested to go, either it's a 2-layer structure or a topological structure information, either with only measurements or with hidden variables actually. Then once the structure is fixed, we'll next move on to the learning, the parameter learning, or you call it the model training part actually. So we are interested in training the particular model part. Okay, yeah. So let me boil down to, like as I mentioned, each node here is a random variable actually. So I'll first write a distribution joint density function of this entire 6 random variables. When I write a joint density function, because I know the structural information, I can easily write individual density functions. I am breaking down a joint density function into individual independent density functions. Okay, so I'm able to construct a density functions. Now question comes, okay, what is this density function refers to? Whether it's a simple Gaussian distribution with a mean, certain mean on variance, right? So that's what we considered in a previous case. Like one can consider a simple, or like each variable, like you can see, I think if you start from y6, so y6 is connected to y4 and y5 with certain variance actually. So I'm considering again a simple linear model. Now I am constructing a model here between these variables by using a simple linear model. y6 equals to some coefficient into ay plus coefficient into a4 plus some uncertainty, because they are uncertain random variables. Again, y5 is connected to y3 with certain random variable actually, because each is random variable, right? So the models that so in the case of regression that we saw before, I was using only one global model to fit between the input and the output actually, one global model. But now here I am looking at multiple linear models actually. Okay, the first model, let's suppose y6, I am going to consider that y6 is a function of, as I can see, y6 is a random variable. So y6 is a function of, let's suppose, a into its parent y5 plus b into parent y4 plus some epsilon, because y6 is a random variable. So I am considering some uncertainty in it actually. Okay, so this is a model structure, simple linear model structure. Now in the same case, I'll look into y5. So y5 is another model which is equals to some c into y3 plus some uncertainty, epsilon 1, epsilon 2. These uncertainties are, this has uncertainty which follows a Gaussian distribution and some mean and some variance, And again you have a different uncertainty which follows a Gaussian distribution with mean, 0 mean and some sigma 2 uncertainty. So like that, I'm going to write for each relation between variable, I'm going to fit a model. When we did a regression, we have only one single model. Okay, we have here a multiple models actually. We are trying to fit a multiple model relation. Is this clear? Okay, so between each variable, I'm planning to come up with a simple linear regression model actually, kind of some linear model. Okay, and now I'm going to use a joint density function and try to fit. This is fine, right? This is called linear Gaussian model. So I can write it in terms of density. Let's suppose if this is a density function y6 given y5, y4, What is the mean of it? What is the mean of this particular function? This is a random function, right? Because epsilon 1 is a random, so y6 is a random variable. So I want to find the mean of it. I just take expectation of it, expected operator. If I take expectation of it, you will get expectation of a into y5 plus. I'm saying that given y5 y4, it's given means it's no longer random. It is constant. Imagine the y5 and y4 are given, means it's no longer. I know that value. It's no longer random. So when I take the expectation of it, it comes down. The mean comes down to be a into y5 plus b into y4, and variance comes down to be the variance corresponds to the epsilon 1, because the same way I can also write a density function of f of y5 given y3, means y3 is known conditionally, so I know y3 information. If I am not assuming that, then y3 is random, right? Actually, so I'm considering that y3 is the information is given to me. If the information is given to me, something which you see or something which is given, it's a deterministic or random? It's a deterministic. So that's why it's a conditional. So I'm saying it's a condition on y3. So it is deterministic. So then it follows, this follows a Gaussian distribution with c into y3 plus sigma square 2. The variance of this particular variable is different, and the variance associated with this is different actually, because it's affecting y6 measurement and this is affecting y5. These are different variables actually. So you have different variances also corresponding. So like that you can write density functions of each variable. Is it clear? Now initially we have written joint density function. Now after that we have written the individual density functions of it. Okay. So the next, so I think I'll just give a step-by-step process for it. So given a 6 variables, like you have a 6 variables, so first I'll write the y1, y2 to y6, a joint density function. So if you can write a joint density function, it is of y6 given y4, y5, and you have function of y5 given y3, and y3 is a function of y1, and y1 is independent because y1 is depending on only its past value, and you have y2, f of y2 is function of y1, given y1, and f of y4 is only depending on y2, and y6 is depending on both y5, y4 comma y5. Okay. Now I written independent density functions, and now I know that y6 comma y4 y5 follows a Gaussian distribution with mean some a into some constant into y4 plus some constant into some b into y5 comma sigma square. This is my density function. I assumed a simple linear Gaussian model. So the relation between y6 and y4 y5 is, I assume that y6 equals to it follows a into y4 plus b into y5 plus epsilon, where epsilon follows a Gaussian. So based on that, I get a density function corresponding to y6 and y5. So I got this density function. Now I'll write down the density functions. So y5, one can assume a non-linear function also here. One can assume a non-linear function. I am assuming a simple linear model here. One can assume any non-linear model. The same thing, how y5 and y3 are related, I am assuming a simple linear model. So a into y4 plus epsilon 1 and epsilon 2, where this epsilon 1 follows a Gaussian distribution with certain mean and variance, and epsilon 2 follows a Gaussian distribution, 0 mean and variance. Okay. So based on this, I am writing a density function of y5 given y4, conditioned over y4. Means I am assuming that we have. So then you get a Gaussian distribution with a y4 comma sigma square. You get one more Gaussian distribution. You get multiple Gaussian distributions for each density function actually. So initially it was, you have a joint, you consider one particular variable and you made it, the samples are independent and made a joint density function. Okay. Now you are, based on the Bayesian network structure, you decompose the joint density into individual density functions. Now you have individual density functions, what is the distribution to it? Okay. So now what should be your goal here? Next, what I'll do? Now I have density functions also. What is unknown here in the entire thing? Sorry? Constants. Only one constant is there. How many constants are there? Many constants are there. So for each density function, you have for this density function, you have constants A and B, and for this density function, you have constants of some C. C is there, and again like that, you have for every density function, you have different constants you need to know actually. So the idea is here, I have a data, that is Y data is there, all the measurement data is there, and U data is also available, input data is available, output data is available. Given the data, can I identify the hidden parameters, the theta? Can I choose best value of theta such that my joint density function is maximized? If joint density function is maximized in the sense, this data is exactly fitting the actual model chosen. This data is coming from that particular model actually. Right? So I am going to solve maximization of likelihood. Again, it's a likelihood function. I call it a likelihood function. Okay, f of y1 to y2 to y6 given theta. Okay, condition over theta. Maximize the joint density function with respect to theta. You get theta hat. This is what I am going to do it now. Maximization of joint density function. If the joint density function is nothing but product of individual density functions, and you know individual density functions follows a Gaussian distribution, and you write the product of individual independent Gaussian function, and you will get a log and take a logarithmic of it. Either you can do maximization of this one or maximization of theta logarithmic of f of y1 to y6. Why we need to do log means because you have exponential distribution. If you assume Gaussian distribution, you have exponential, you'll get a nice simple explanation form. That's why you do a log of it. Okay. So is it straightforward now? For the maximum likelihood case, only one parameter was there. You maximize and theta. But here you have n parameters actually. You get multiple parameters. You need to do first order optimality like gradient, finding the gradient. Multiple for different parameters, you'll get different equations. Okay, that's fine. I'll make it more complex. Okay, this is okay? You understood, right? You have a structure. Now you assigned a model to it. Each model now I assigned for each interaction. I'm assigning one linear model. Okay, rather than one global model, I'm assigning one linear model and writing a joint density function, and I'm maximizing the joint density function with respect to theta. Okay, find the best value of theta such that this density function is maximum, at which it is maximum. Okay, so that's what you want to do. So you'll get when theta is optimal, you'll get the probability equals to 1 when the error is 0 actually. Right? This is fine. This is straightforward a likelihood problem. We call a straightforward likelihood. Only unknown is theta. Only unknown is theta. Only the parameters are unknown. The model parameters are unknown. Now I'll make it more complex. Let me see what is the solution. So these are the parameters. This is the joint density function. Okay. For this system, this is the joint density function. Okay. So now I say that I want to solve this one. Is it the same? The previous case and this case? What complexity you get additionally here? Initially it was probability of these nodes are all known nodes, means they are all measurable nodes. Okay, so I will write only the probability of y given theta, that is the joint density function of individual data. But now I am saying that not only you have known measurement nodes, you also have hidden nodes. These are the hidden variables actually, which are present inside. So actually, let's suppose you have a sensor. Okay, sensor is actually fluctuating, but actually the hidden variable is this one. Hidden variable is lying here actually. Okay, so let's suppose if I am not filtering this out, okay, and I'm only sending this signal to predict certain model, my model predictions are completely wrong. I wanted to actually come up with this hidden signal actually. I want to extract this x to it. So what is the complexity that I get now? What are unknowns? What are unknowns, additional unknowns? Initially it was theta, parameters were there. Now? Hidden states, you also have hidden states actually. X is coming now actually. X is random. We are assuming that X is the hidden internal state is a random variable and it is unknown. I don't have any idea of it, what it is. Okay, so there is, this all pink are all hidden nodes. I don't have any idea of it actually. Only these are the measurement nodes. Y3, Y4, this is the measurement information available. These are the hidden nodes. So I'll get additional complexity of not only just like similarly, I'll assume here also between the variables, it's again a linear model. I assume how I assumed previously. Between y6 and x6 is a linear model and x6 is also a linear model. Okay. So based on the structure, I can again decompose the problem as a, now I have y1 to y6 and x1 to x6. So how do I decompose this one? I'll start from down. I start from one particular, from down variable. So I'll start decomposing from y6. So y6 only depends on, y6 only is depending on x6, given x6, y6 is depending on x6. Then x6 depends on x5 and x4. Then I think x5, that means the direction is towards this side, right? And then y5 depends on x5, y5 depends on x5. Okay. So probability of function of y5 depends on x5, and then you have x5 depending on x3, function of x5 depending on x3. So the arrow which is coming out, we wanted to, that is what we are interested, y3 given x3, and you have f of x3 given x2, x1. And you have y1 given x1, f of y1 given x1, and x1 is independent variable actually. Okay. Yeah. And then you have, again you come up into that leg. So now you are getting additional density functions actually. So you not only have measurements which are known, now you also have a hidden variables density function. You need to know hidden variable density function also. If that you don't have any idea of it, what is the hidden state? Okay, measurement, at least you know what is a measurement actually. You don't have any hidden information part of it. So one can consider the relation between the parents, like the hidden variables, as it's the same Gaussian distribution with a constant mean and some parent, like the linear model. Like let's suppose for the case of x6 and x5, I'm assuming that x6 is a function of some alpha into x5 plus beta into x4 plus epsilon, I'm assuming. So if I write it in density function form, x6 given x5 comma x4 follows a Gaussian distribution with the mean is this one, alpha into x5 and beta into x4, and variance is sigma square. Just take the expectation of it, you will just get the mean of it and the variance of it, okay. So this is what the model that I'm choosing. I'm simply choosing some linear models actually. One can choose non-linear models, it becomes much complex. So it's choosing a simple linear model between the hidden variables, okay. So like that you get a joint density function. So your likelihood, your joint density function now looks like this. You not only have variables with respect to y, you also have x variables, okay. So when you're trying to maximize this density function, now what are the unknowns? There are two unknowns, theta and x. I have theta as well as x. Can I do it together? I think it was wrong. I should have written x also here. Maximize with respect to theta and x. Can I solve it directly? Let's suppose you have 2 equations and 4 unknowns. What do you get? 2 equations and 4 unknowns. Can you able to solve? You can't solve. This is a problem of the same thing actually. Now you have less than, once you do first order optimality, you will get, when you differentiate with respect to theta, when you maximize with respect to theta, you are going to get a certain equations where x is also unknown actually. There are parameters of theta and there are parameters unknown. So I cannot directly solve this problem as a, how I solve for regression, how I solve for the other case. I cannot directly solve this problem. Okay, it is not just a straightforward maximum likelihood problem. Okay, so you need to solve by using something called expectation maximization algorithm, EM algorithm. You need to use EM algorithm to solve this problem. Okay, so the complexity increases because initially when we solving, we had only measurement nodes and the only parameters that are unknown are the model parameters between the variables. So only the beta, not beta, these are the unknown parameters that you can directly solve by maximizing write the joint density function and maximize it. But additionally now you are getting the hidden variables also actually. So when you write the joint density function of it, so then you will end up with intractable solution. You can't get an analytical solution actually. What is x and what is theta? You can't get an analytical solution. But I want to solve this. How do I go? Okay, so expectation maximization, I think even electronic students who are background who have done PhDs and all, it's widely used in signal processing because you have hidden variables there actually. Okay, so in Gaussian mixture models or any process where you have hidden variables and you have measurements and you want to estimate the hidden states of the system. So you use expectation maximization algorithm. Okay, so let's see what is this algorithm part of it. Okay, so yeah, when you write this joint density function, expanded by using this all dependencies from the structure, you are going to get that structure. Okay, so you are going to get this particular structure where xc corresponds to the final value and the likelihood depending on measurement and states, independent states. Okay. So I want to now maximize this joint density function with respect to theta, but x is hidden, x is unknown. So I want to somehow find x value. If I fix x value, the problem is straightforward. It's a same likelihood problem. There is no difference. If I fix x value, if I know x value and fix it, then it is just maximization with respect to theta, right? I should fix the x value, but x is random variable. So EM gives a very elegant way of solving expectation maximization. I want to find what is the value of x such that if I fix it, I'm fine. Okay. So what I'll start with, theta is also unknown, x is also unknown, right? I'll take some theta guess. Okay. I'll take some theta guess and I'll find what is the expected value of this joint density function. For a particular value of theta, what is the expected value? Means it's not absolute value, it's correct value, it's expected. What is the possible value of it? What is the possible value? So I do an expectation of log of joint density function. Okay, I do an expectation of joint density function. When I take this expectation inside the operator, okay, you will get it's a derivation. It involves a lot of derivation here actually to get it actual cases. So you have an expectation, you send the expectation operator inside the log of this particular function. So then you need to find some expected value of x actually. What is the mean of x actually kind of, okay. So mean of x given particular mean and theta values. So once I know expected value of x means it is fixed, it's a constant value. Once I fix the expected value of x, then I will maximize this q function with respect to only theta. X is fixed, I will only maximize with respect to theta. Okay. Overhead, it's gone. it's out of the campus actually, ball. Okay, I think it is too much for you guys actually. Means I understand. Yeah, this, but I want to just give a gist of it. What involves when you get into probabilistic thinking? What are the challenges involved in probabilistic thinking? Okay, so these are the challenges which you get it actually. But you have nice. See, I am addressing the problem of noise without any issues. I am just addressing this issue where I can't address in regression. When I do a regression, I can't do this problem actually. Yeah. So I need to either use some filtering, pre-processing or something like that. But I can inherently address this. But the problem that I am going to get it is a challenge, a challenging problem. I need to solve this, maximize this with respect to theta, get this one. Okay. So it involves two steps. It's an iterative process. Rather than solving an optimization problem using any optimization technique, we are using this technique, where first you fix x, find the expectation of the joint density function, and fix x for a given theta. Once I know x, then only unknown is theta. Then I maximize the joint density function. That's what here I'm doing. So when I do the expectation of it, you will get this kind of some terms you need to know. It's a nonlinear function. You need to expand, send the expectation, find the unknown variable, and get this expectation terms. Once I know these expectation terms, the next which I do is the maximization. Okay. So there involves again the problem is expected value of x is what? Mean. It's a mean, right? I need to find the mean. So I use some posterior distribution and try to find the mean of it actually. Okay. So I use some Bayes theorem here and try to find the mean and variance of it. So that's what here I'm going to use posterior distribution inside the E step. Inside the E step, it's a x is a random variable. So you need to find the mean and variance. So I'll use Bayes theorem to find mean and variance. Okay. So then once I fix it, the only problem that I have is theta. I maximize q. I maximize this with respect to theta because x is fixed. X I already known by using Bayes theorem. I got the x value. I used it. Then I maximize. I'll get the updated value. Then I check whether the updated value and the previous theta are decreasing or not. If they are decreasing, I'll stop. My iteration is stopped. That is a theta. If not, I'll again go back and I'll change the theta value. Find x. Again maximize q. Change the theta value. Find x. Again maximize q. Until unless the theta gets converted. It's an iterative algorithm to find the parameter values theta. Okay. So by fixing x is being fixed actually. Okay. I try to get the x by using Bayes theorem. That's what the idea is. So this gives, I think, you choose some parameter theta. There is E step. The most challenging step is E step because you are going to find the expectation of the joint density function, which is a complex problem where you take the expectation and find the mean of it. So finding the mean is again going back to finding the Bayes theorem and using the Bayes theorem and getting the information of it. So it involves that problem. Yeah. Yeah, and once this is x is estimated in this step, that x goes to m step. Okay, and you might do the maximum likelihood problem. The same thing. Use the steepest gradient descent or any optimization problem and solve it. Okay. Yeah. So yeah, this problem arises in the case of multiple domains. Actually, in the case of chemical engineering, like you are taking one particular sensor and your hidden variable is something hidden. You doesn't know what is a hidden variable inside. You need to estimate the hidden value theta because the actual sensor is giving noisy. I want to estimate the hidden theta. So how do I estimate it? One way is do filtering, Kalman filtering. So actually what we are doing is kind of a Kalman filtering only. It's data-driven Kalman filter kind of. If you actually derive it, every equations, you are going to get a Kalman filter, nice Kalman filter. It's a steady-state Kalman filter you get. Or if those who have idea of Kalman filter, you can appreciate it. You'll get a steady-state Kalman filter. Yeah. Okay, so yeah, in that way you maximize and get the theta. Okay, so let's suppose you have done this. You got the parameters. You estimated the parameters theta, and your network structure, everything is known. Okay, means you have estimated the parameters between this equation. You know what is this equation, and all the parameters are known among them. Now you have entire structure is there. Okay. Now I am interested in order to predict x. What is my true state? I am interested in predicting x6. X is a random variable, right? If I have to predict this, if it's a random variable, you need to get mean and variance of it. Then only you can able to characterize it. Mean and variance. So I'll use Bayes theorem. Everywhere I use Bayes theorem. Bayes theorem everybody would have studied, right? Probability of A given B equals to probability of B given A into probability of A by probability of B. I'm just going to use the posterior, but for that particular term. Okay. So this is called inference. So I use Bayes theorem and I compute posterior distribution. So this is a posterior distribution where I'm trying to find the hidden state information given the measurements. I'm going to estimate all the hidden states of all the random variables given measurements by using the likelihood and prior. This is called prior and this is called the likelihood information. Okay. These are all Gaussian distribution. Now you have estimated all these parameters here. In the previous step, you have estimated the probability of, what do you say? Go back. So you have estimated all these parameters relating the x, these all variables actually, these all parameters are known. So everything in the inference step, inference is prediction. When a new measurement is coming, you are trying to predict what is the hidden states in it. So I'm using posterior distribution. I'm using Bayes theorem to predict the states, internal states of it. So this does this posterior distribution. Okay. So this way Bayesian networks can help you handling noise in the sensor data without using any pre-processing. You are trying to construct a network structure, adding one more hidden random variables, and can come up with the hidden state information, actual true state information. Okay, so you're doing it. So how do we do that? By maximizing the joint density function. Now it's not only with respect to y, with respect to x. So this is for the case of noisy data handling. When you have a data is noisy, you are going to write this joint density function. Okay, so how am I going to maximize the joint density function? I am going to maximize by using the EM algorithm. 2 steps. I do parameter learning in E step and M step, do this training, get the parameters theta, and do a inference. Okay, I'm going to do Bayes theorem and do the posterior inference computations here. Fine. Yeah, this is when the noisy data is there. Then we discussed in the first class in the morning session that when you have missing data, let's suppose one measurement is coming at multiple data. What did we thought? Downsample means select only the samples of that particular variable. Now, if you go back to our previous slide, I just go back to. I understand it's a bit heavy, but I just wanted you guys to get exposed to the Bayesian viewpoint. It's so this was the case which we discussed, right? This case we discussed, where in this case, what we were doing, we were only selecting the data points corresponding to this one, and data points corresponding to this one, and data point, input, output, and fitting the model. So we are losing a lot of chunk of data right here. A lot of data is missing. I don't want to do that. So what I want to do is, I want to retain this. This is my input, retain data, and these are my output, right? I want to estimate these variables. This is called missing data problem. The data is missing. Can I treat that missing data? Missing data, I don't know what is the thing. I'll treat that as a random variable. I'll treat these all variables as random variables. Random variable problem. And I can solve it actually using Bayesian networks. Okay, so I can, in addition to the hidden states, I can also consider the other hidden state that is present is missing data. Why missing data is one more hidden state which is present. And I'll try to again do the expectation and try to estimate the hidden state and estimate the theta. So yeah, this is, so in this case now you are missing data, you have measurement data, observed data, some is observed and some is missing. Okay, so missing is, I am assuming it as a random. When I assume missing as random, so now y is not only just observed, you also has a missing. That is also unknown. Y missing is unknown, and x is also unknown. Actually, theta is unknown. It becomes, you are increasing the complexity of it, but you are actually not removing the data set. You are actually considering the full data part, and your full inputs are completely. You are not downsampling it. The data is complete full. You are only select the missing output variable. You are considering it as a random variable. Okay, missing output is random variable. I am not deleting the data. Okay, I am completing full data. So that's actually this is a nice way of solving using EM algorithm. EM has been developed, it's developed by Dempster in 1979 actually. It is used in any area of engineering. This problem is very common of missing data information. I want this, because if I delete the data, what is happening? I am losing the information density function will be of this nature. Joint density is of this nature. You have y observed, which is constant because you observed the data, and you have missing data which is random. Okay, and you have x which are random variables present, which is random, and unknown parameters are theta. Okay, so I want to do this. It becomes quite messy. The most challenging step is this one, doing the expectation of a joint density function. You have to do the logarithmic of this function, expand it, take the expectation, send the expectation inside, and find the mean of expected value of x. Okay, again you have to go back to Bayes theorem and get the pull data from there. Okay, so I'm just giving an idea. Go back when you are trying to do your research, or somebody actually you can just pull the Dempster paper. You can see Dempster maximum likelihood estimation or EM algorithm, or Moon TK Moon is Moon EM algorithm is a standard paper. It's a very simple way of explaining. I think it's for image processing. He has done it. So it's a very nice paper to look into this one. Okay. I'll just take one example. We have solved it actually. We have used, it's not only just theory, we have actually implemented this in a case. So yeah, So the problem here is for this case, any doubts? Okay. Sorry. Ah. So that's what, see, whether there are filling, that's what, there are two ways of filling the data, which we started in the morning session, which we have discussed. One way is whatever the previous value which is there, let's suppose if the frequency of sample is very less, every 1 minute you have samples and some samples in between they are missing, you are getting none. Then you can use previous value or average of previous value and do it, time series average, or you can do it. Let's suppose you have frequency of data is very long. One sample is coming at 1 hour, next is 6 hours, 7 hours. I can't use previous value, right? Because you don't know what is happening here. So in that way, one way is to do downsampling, only select the measure. Don't select the NaN data, remove that entire column, entire row. If you have 10 variables, if there are NaN for a longer time, just remove entire data sets. That is called downsampling. We are sampling it only when the measurements output variable are good and considering it. The other way is use EM algorithm and try to estimate that hidden variables. I don't want to delete the data because data is crucial. There is a good information. I want to estimate that without deleting the data point. Actually. Okay, so that is, yeah. Okay, so I will just show you to one example case study. So this is a process, any industrial process it is. Actually, you have an output quality variable and you have several inputs which are affecting the output, okay, output. So we have considered two different structures which are topological structures. We do not use any data. One can use score-based algorithms which you can find in a BN-Learn toolbox. When you use the toolbox, it gives a structure, it gives the parameters also. It does everything once, together training and structure parameterization. But you can't do all these things. You have to, if you want to do this hidden variable information, you have to write your own code. There is no availability. Okay, what are the BN-Learn toolbox which is there in the MATLAB or this one only has the conventional way. That is, all variables are known. It tries to find the structure and learns the parameters. But if you want to do this hidden variable information estimation, you should write your own code. Yeah. There's no code available here. Okay, so we have come up with two structures. One is a two-layer structure, which is like saying that all variables are affecting the output. Excite is the output desired, and all variables are affecting the output variable. But here we are assuming that some variables are noisy data. Some data which is entering into the process here is noisy data. So we wanted to filter out that noisy data points and come up with a true state. Similar way, and one more structure we came up with this is by using correlation analysis, we came up with this. Here also we are interested in order to come up with the noise-free estimates of it. Okay, we did joint density function and all. So you can see that the performance when you use the same data to regression, OLS, ordinary, are getting much higher, better correlation. 76% we are getting actually. Same data set used for regression, we are doing the same regression here, right? Doing the same regression, but that you are using hidden states actually, kind of, and filtering out the noise or unknown components actually. And doing the performance is increasing actually. That means it will have an effect of it. Yeah. Okay, but if the same problem is in regression, then you need to do some Kalman filtering before and apply it. You can't directly modify your regression problem. So Bayesian network gives that scope because we have formulated as a probabilistic version. Then you can able to solve this problem actually, because you are assuming that a hidden variables and you are using the joint density function to maximize and doing it. So that's a one elegant way of solving the missing data or noisy data problem actually. Yeah. Okay. So I think I'll conclude. I think here we can see here what is the difference between Bayesian network and Bayesian neural network. There is something called Bayesian neural network also. You would have studied the basic neural networks in the previous class, right? There is something Bayesian also. We can also think of Bayesian version of it. What is the basic difference from image? What you can understand? Bayesian network you have, Bayesian neural network you have. What is the difference? Weights are Gaussian. In the case of neural network, you can see that the weights, the nodes are not random. They are deterministic. The nodes doesn't have any randomness in it. The nodes are random actually. The weights associated with the connections are Gaussian actually. Okay, so now we are assigning some uncertainty, some distribution to the weights actually. Okay. So, and then how do you solve the problem? Solving the problem is the same. It's much more complex now. This case is much more complex because you have more number of hidden variables, more parameters. So writing a joint density function will be killer. I don't know how you can write it down actually. We need to see this one. So this is secular. But in the case of Bayesian network, you see that each node is variables, random variables, and the direction that is given. The direction is important here. Here you don't have any. The direction is you are not connecting any process knowledge here, but here you are using some process information actually. So we are able to connect through the flowchart. Okay, but the only difficulty here and there is it's a non-linear problem. Here it's a linear problem. We are considering a linear problem here. Okay? Because the model that we have considered between two variables or three variables is a linear Gaussian model. Okay, one can use a non-linear model also between them, but it becomes challenging. One can try. One who are PhD students are doing it can try thinking of considering a non-linear neural network problem. That can be a good problem to solve. Yeah, that's a basic difference. Or else, I think Bayesian networks give the visual representation of cause and effect relationship between the variables actually kind of so that gives a good idea of it. Yeah. Fine. So yeah, if you have any questions, you can ask me. I think it's overhead on last day afternoon. I think I'm teaching the toughest topic. I'm not sure that it is. You have a lot of methods to obtain the structure. The structure identification is a challenging task. You have methods, the score-based methods. They use genetic algorithms to identify the score. You are trying to maximize the score. There is some function which can maximize the score. Means let's suppose I'm trying to fit x1 to x3. If I'll show you the diagram right now. I have the that takes at least 1 more hour in order to teach that. So I'm not keeping that structure learning. Structure learning is the toughest part in Bayesian networks. But I can just show you, give a glimpse of that part. Right? So you have these search-based algorithms. Oh. So these are score and search-based algorithms. So it will solve some. Yeah. So you will have this BIC Bayesian Information Criteria score, depending upon the score actually. So it will keep trying to search which is the best maximum score that I get between the different relations actually, and tries to freeze a particular structure depending on identifying the score or the structure actually. Score-based algorithms, you can look into score or search-based algorithms. So you already have the toolbox which is there in MATLAB, BNT. I think you can look into Kevin Murphy. Kevin Murphy. He has in his site, they have developed this toolbox, BNT toolbox is available, Bayesian network toolbox, BNT toolbox in MATLAB, it is available, I think even in Python it is there, Kevin Murphy, probabilistic graphical models, you have thesis and all this. This is one interesting area to explore so that you will get it, yeah, okay. Yeah, if you want to do any additional things, there is a lot of openings here. I think people are not done in terms of time series data. There a lot of work has been done in terms of fault detection. Use of fault detection, a lot of work has been done. Yeah. Okay. So I think with this, I think I'll pause here and I want to discuss some applications. Are you guys ready? Ah. Okay, applications is ready. Yeah. You wanted, yeah. Okay. I think these are generic applications, may not be this one towards Bayesian networks. We will get into some examples where you use predictive models, like where you are going to use predictive models in different areas of engineering, we can look into it. So whatever we looked at previous was global modeling. Means you have entire data, you're taking entire 80% of data, training the data and predicting it. Okay, that's a global modeling. You're using global modeling. Okay, so there are different kinds of modeling. One is global, where you have entire historical data, train 80%, 20% and train the data. And there is something called local modeling. Okay, so I'm not interested in coming up with a bigger model. Can I come up with a local models actually? Okay, so around that particular point which I'm desiring, I'll only consider to develop a model, local model, predict, discard, again consider, go to a new point, search the nearest neighboring points. I use KNN search. I think KNN search is demonstrated in this size, right? Yeah, you use K means KNN nearest neighboring search algorithms, get the nearest neighboring points, build a model and more. So that's called local modeling. There is something called ensemble modeling. Ensemble modeling is a combination of two different models actually, a multiple model approach, or not one single model. You are going to use multiple models to develop a model. Okay. Yeah. So we'll just go upon some examples which you have worked on, kind of actually. So yeah, this is one example of we use local modeling. This is a nice example which I worked on. I'll just give a demonstration of it, where we are interested in predicting the ore characteristics, quality of ore in a industry, in a mining industry. So what is the quality of the ore which is coming from the process? So can we able to accurately predict the ore quality in real time? So you'll see what is the challenge here actually. So this is typical what this oil sands industries, where you get mined oil sands from the top. Means it's a mining area. You go, the trucks go, they mine, they get the ore, extract the ore, taken in the trucks. This trucks gets into the refinery. The sand gets into the refinery and they crush the sand and extract bitumen. That bitumen goes into the the further processing of extraction of crude oil. Okay. Okay. So when you are extracting, getting this mined sands, the problem is the ore quality. The quality of the ore is critical. If the ore quality is poor, so you are sending that ore quality into this particular multiple process, and there is something called pipelines are there, transport pipelines. If ore quality is poor, this gets clogged. If this gets clogged, there is no feed to this. If there is no feed to this, there is no product coming to this. Okay, so entire things get stopped actually, kind of. So it's a huge economic loss actually. This gets clogged. So why this gets clogged? Because there can be, if ore is not measured accurately, then and you means at different layers, when let's suppose you are mining at a one particular surface, at different places the quality of the ore is different actually. Okay, so it's if we know that what kind of ore quality I needed at this particular place, or in real time you can provide an information to the truck operators or mining engineers, that can be helpful for them to take a decision actually, kind of, and operate the parameters in the process accurately. So I need to know real time ore quality measurement. So here we just use some local modeling approach. We'll just demonstrate what is local modeling approach. Okay, so this is like a mining surface, like this is a plain surface. Okay, this is a mining surface, and I'm interested in this part. I'm interested in this location. I want to know, because the vehicle keeps shifting its position. It's not one constant. It keeps shifting its position, and it has to know the ore quality at that place actually. Okay, so and they have only limited samples like this. These are called core samples, means like lab samples. Okay, only once in a week or once in a month they select these samples and find the ore quality. So only these samples are available. Okay, and there is some model which is available for them, which can provide some information, real time, some information. So I wanted to estimate the ore quality or variable quality here. Okay, so should I take entire data and model this point, or can I only consider the points nearby and model it? The easiest way is I'll just consider the points nearby and model it, because the process conditions are keep changing, the locations keep changing actually. So that's what we call local modeling. So where I'm here, I'll only search the nearest points which are around it actually, rather than considering entire global point, which can be suboptimal. So I'll only consider the nearest neighboring points. How do I get the nearest neighboring points? I use KNN search. What are the distance-based criteria? I use Euclidean distance, search the nearest data points, pull the data points, get the input data and output data, and fit a model between. But in the global model, you have input-output data. Only one data set is there. But in local modeling, for this particular set point, I will get approach, which is is widely used For the case of like time varying process conditions are continuously varying. So we use this local modeling approach significantly. This is one good application of machine learning in a mining industry actually. You can call it a mining industry. It's a good application of machine learning in mining industry because one global model doesn't survive here. You need to go with the local modeling approach actually. This is one more model. So I think we have this one. You can see this. These are the actual, the red values are the true or the model which they have a global model predictions. These are the global model predictions. And the blue which is are the local model predictions. Local model is able to actually capture the true variations accurately. Right? Yeah. So then we have, I'll take this is more interesting. So which our students are working on it actually kind of. So this is soil moisture predictions actually kind of. Okay. So in the agriculture field actually, I think nowadays we have this digital agriculture. Digital agriculture is more common, right, actually. So you wanted to optimize the water to your field. Optimize the water to your field. How do you optimize the water to the field? By measuring your moisture, soil moisture content. If you can measure the soil moisture content or estimate the soil moisture content accurately, you can actually optimize your irrigation. It's a closed loop control problem. It's like you measure the through sensors, you measure the soil moisture and take signals to control your irrigation, how much amount of water is sending. So here the focus was on predicting the soil moisture. It's again the soil moisture. The problem is the same. It was mining. It is agriculture, but the thing is it's land. It's on the land, and you wanted to predict moisture now. Initially, we were predicting ore quality. Now we are predicting moisture actually, and at different locations. Same logic we have used, the local modeling logic actually. So that was that really works. We have taken some data sets of European data sets and use a KNN search algorithm part. So you can see that the autoregressive model. I think in the morning we discussed autoregressive model, right? What is autoregressive model? Yes, okay, that's good. Okay, something has got in actually. Okay, so we used autoregressive model, and we can see that just a regression model was very poor. Even local model regression model was out actually. It was only giving r square fit was around 0.3. But when we use the autoregressive nature, using some features of past features data, performance was huge jump actually. Kind of. It was a huge hit. Okay. Yeah, even the nonlinear regression is a linear. I think global model failed completely. Entire modeling of entire area, soil moisture, it failed completely. We can't use a global model. So we used a local model. So that was giving 0.3 and ARX, autoregressive models works well actually. Okay. You should use, when you are using it, just don't go blindly using of regression. Okay. Try to see if you can get some autoregressive nature's inputs also kind of that those adds additional power to you actually. Okay. This is related to agriculture and one example related to pharmaceutical industry. So in the pharmaceutical industry, like you manufacture this penicillin production. Okay. When you manufacture this penicillin production, the sample which you collect is available only at every 6 hours. Okay. I wanted to estimate the real-time penicillin production. I want to monitor it. If I monitor it, because I wanted to maintain the real-time penicillin production as 99% purity or something. I want to really monitor that. So here the objective was to use some deep learning models. We used some deep learning. We have around, this is a large scale problem. The variables are around 15 to 20 variables are there. Then we did some correlation and bring down the variables to around 10, 5 to 10 or 14. The variables are around 25 I guess actually. We brought down to lesser number of variables and use deep learning models to predict the real-time, the penicillin production process actually. So this is a real-time penicillin production process. So here we did multiple predictions of the variables actually. Okay, so this is related to pharmaceutical industry part. So we are, and then I think this is the last one example which I can show. This you can get a feel of the areas of engineering that you can dwell into, what problems that you can handle it. Means what the techniques that you have implemented on mining, you can implement on agriculture. Also, if you can able to understand the right problem, you can actually take that and put it here actually. Understanding the problem is a thing actually. So the last is, I think this is one interesting work which we are doing currently, is marine heat waves. So we have seen heat waves in the land, right? the temperatures shooting up actually. Last week or 2 weeks before, the temperatures are very high. The same heat waves happen in the ocean also actually. Okay, when the heat waves happen in the ocean, the sea surface temperature rises significantly. So what are the effects of it? The heat waves are coming in the ocean. What are the effects of it? The underground flora and fauna gets, okay, there's a huge fishery industry which is surviving on it actually kind of, okay, so where they cultivate artificial fishes, not artificial, they cultivate fishes by using cages actually under the water. So when the temperature goes up, there can be the fishery industry can significantly get affected, especially in the case of Western countries kind of actually. So I think one kind of situation happened in 2014 in the Bob where they are not able to predict that heat wave. That heat wave devastated complete that particular coastal in the Pacific coastal areas actually. Okay, so early predict, can you able to predict this heat wave early before 10 days or 15 days? If I can predict the heat wave early, which is happening on the ocean, is beneficial for me, right, actually. Or I can send it to the coastal economy, people where they can make the necessary changes actually, kind of, okay. So this project was like heat wave in the sense when if the temperature goes beyond certain critical value, then it's called a heat wave actually, okay. So here we used deep learning, again we use deep learning models. One can use deep learning models actually. So to predict the, you're able to detect the heat waves at least 5 days before ahead actually. So you're able to detect the heat waves 5 days before ahead. This is one example, and there is something I think yesterday Professor Bhushan was discussing about transformer models. Okay, so we use transformer models like time series. For transformers are generally used for language NLP, okay, natural language processing. Okay, but one can use for time series data also. One can use do long range predictions for time series. So if I want to predict weather conditions for the next 1 year or next 10 days or 15 days or 1 month, okay, I can use this transformer models. So here we have done some analysis, initial work, where we are predicting that sea surface temperature for a 5 days ahead forecast and 15 days and 366 days ahead. You can see that the models are, we are shocked to see that it's a 366 days. I'm at here, I'm not using any future data. I only train the model and I'm predicting for next 366 days. Next 366 days, so not one time, 366. So you're able to completely capture the trend of it actually. Okay. So they're powerful models. I think when you want to do long range predictions and forecast, these models are very excellent actually to use it. Okay. So I think it's excellent. I think can want to stop? I go. 10, 15 minutes. Okay, okay, okay. I think they can't take it. I guess they are done actually. I can see their faces. I'm just putting it. So I think identifying the problem is critical when you're using this large language models or something like that. Which problem where to use is identified. So here we use for long range temperature predictions actually. So this is good critical result actually. Yeah. Yeah. But I have not have any example. Yes, ML it has come out from the gaming. Like if you look at reinforcement learning, it has come out from the chess actually kind of. So it has beaten AlphaGo or whatever it is actually kind of. Yeah, they use a lot of ML in gaming industry kind of. Yeah. Yeah, but where we get funding for the institute is from the industries. Right. Whatever your question is correct actually, but whatever the examples that I can show is the industry examples because we get funding from them, right? That's good. Yeah, I think they do a lot of this artificial chess, like computer-based chess. They use this all advanced machine learning algorithms actually kind of. And they predict before what the step that you're going to take and do that. Yeah, that's true. The gaming zone, yeah, it's there. You can explore in that. Yeah, its future is there, but the sponsors should be there actually. We will fund you, right? Yeah, that's the thing. Yeah. Okay. So, yeah, I think so. That's good. I think there are a lot of things. I think I can stop over here. You can ask me any questions. I think I'll just stop over here. There are a lot of other things. But yeah, I just want to give some probabilistic touch and some examples, case studies of whatever it is. If you have any doubts, anything you want to share, then we can discuss. Yeah. Yeah.
We are chemical, but we do a lot of maths. Everything background is maths, right? You agree? Everything background is maths. Actually. So we are in control. So we are exposed to hardcore maths. So and I think machine learning, once you get into data analytics, you see data. Right? This is any system. Understanding the physics of the other process is also important. You need to spend some time there. It's not that easy. But I think data analytics is that field where you can actually land into. So that has gave us more flexibility to land into other. Not a larger. I'm not taking global model. Global model is entire data. I'm taking only that data points and local going on. See, when I went down, mining is first I'm interested in this particular course. Now I move to a new course. When I move to a new position, the model that you develop here will not work well. Again, I go and search them, develop a model and predict. And then again, I move to a new position. Again, I search local points. It's a global model. Every time I'm selecting a new model, thousands of models will be there. But you will discard. You won't save it. You won't save it. You keep on changing the conditions. You keep on going to new points. And one place use global model.